Hello, welcome once again to my YouTube channel, and today I'm gonna show you about. Hello, welcome once again to my YouTube channel, and today I'm gonna show you the presentation for my digital logic design project, and I will explain all the aspects like how we designed it, how we made it, and the finishing part of our uh, project. So basically, our project was a line following robot. Pardon me, I just made a mistake over here for the spelling. So, line following is one of the most important aspects of robotics. A line following robot is an autonomous robot which is able to follow either a black or white line that is drawn on the surface consisting of contrasting color. So, it is designed to move automatically and follow the plot line. The robot uses several sensors to identify the line, thus assisting the robot to stay on the track. The array of four sensors makes its movement precise and flexible. The robot is driven by a DC gear motors and by the control of the wheels. So basically, here in our project, we had some sensor placed on it, and we made a line following robotic car. It was consisting of some sensors on it and two motors, and was run by a motor driver. And it has multiple connections on it. We can use breadboard too for the circuit implementation, but here for more simplification and for making a smooth and good looking precise model, we use PCB board. So here was how our project was. Here were some connections with our PCB board. This was the motor driver, and these were two wheels, and they were connected. So there were some ICs that we used. Some ICs which included 7404. Here 7404 is a not gate IC. This is 14-pin DIP version of the popular NOT gate IC. 7404 is NOT gate IC. It consists of 6 inverters which performs logic inward action. The output of an inverter is the complement of its input logic state, which means that the input is high and the output is low, and when the input will be low, the output will be high. So basically, it is an inverter gate. When the input will be zero, which means that the system will have a low input, the output will be high, which means that it will be giving 1. So this is an inverter gate which is used to invert the values in between input and output. The second main IC that was used in our project was 7408, which is basically a NAND gate. And in simple words, NAND gate is basically the not operation of AND gate, where AND gate has function that if both the inputs are high, then the output will be high, and if either of any input will be low, then the output will be low, which means that if 0 and 0, then output will be 0. If 0 and 1, the output will still be 0. But when the both inputs will be 1, then it will be 1. So if we look towards the through table of AND gate, which will be like, let me show you that. So here's how the diagram of circuit diagram of the AND gate will be, where two inputs are given, and it is represented by a round shaped gate like this. And when this is the truth table where two inputs are 0 giving 0, and when the both inputs will be high, the output will be high. So this is the simple circuit diagram of AND gate um, uh, and the truth table of it. Now, when we look on to the NAND gate, so let me show you NAND gate 2. So here is the NAND gate where when two inputs are given, it will have same operation as AND gate, but it has an inverter in over here which will invert the values of AND operation. So when the input will be 0 and 0, it will give 0 in NAND operation, in AND operation, but we will give, but we will get 1 in output because it is inverting the AND operation. So basically the NAND operation has through table like this: when 0 and 0, output will be 1; when 0 1, output will be 1; when 1 0, the output will be 1; and when 1 1, the output will be 0. So that was the gate that we used here. Now the last one was 7432, which is the IC number of OR gate. So OR gate consists of four OR gates. It is basically an IC having four OR gates inside it, and the OR gate performs logical OR operation. So OR operation has three terminals and two inputs and one output. So basically when we see towards OR gate, so OR gate will have the circuit diagram like this, um, like here. This will not circuit diagram, but like the symbol of the OR gate is like this. And when we see the truth table of it, so we can see when both inputs will be low, the output will be low. But if either of two inputs will be high, then the output will be high. Like 0 0 will give us 0, but 0 and 1. Now here this input is high, so it will give us 1. So this is the um, truth table of OR gate. Now coming back here, we use another IC which was 7411. So 7411 is IC which consists of multiple AND gates. So I described the AND gate earlier. So that was the ICs that we used here. Now after it, we will I will describe you what PCB etching is. So PCB etching is the process that uses chemicals to make proper traces to connect different components on the circuit board. So basically, we have a PCB board, and we go to Proteus to design the circuit as per our requirements. Here, what the Proteus interface looks like. Here, we can choose different um, components as per our requirement by typing here. Like, let's say if I need LED, so I will just type LED, and it will give me multiple LEDs over here, which we can use and implement in our circuit. So here it is the interface of Proteus. We will just go here, and then we will have to draw PCB design. Then we will just select an option of turning it into PCB and we'll connect the wires. So coming back to our presentation, PCB etching, the copper is removed from the board, and then we will use ferric chloride chemical, like 2 tablespoons will be enough with in a water, and we'll make solution and we'll dip the PCB board into it to get some proper etching of the circuit. So basically I will summarize the whole process here, that we first of all go to Proteus, we design our circuit, and then print it on a butter paper, and then we place butter paper on the PCB board which is fully made of copper, and then place iron over the butter paper and just move it around for some minutes. That will transfer the whole circuit that we drew on the butter paper to the PCB board, and when it will be transferred on PCB board, then we'll just dip it into the solution so that the path that is drawn on the PCB board will remain, and the other copper will disappear by having a reaction with ferric chloride. Um, and we will keep the temperature up to 55 degrees Celsius, and this reaction is also exothermic, which means that it will emit some heat too. So when we'll heat the water, so it will just boost up the speed of our reaction and will remove copper more swiftly. In normally this reaction takes place in between some 15 minutes or maybe 20 minutes, or if the water temperature is low, it can take some more time. So when the PCB when the etching will be done, so we will use drill machine to make holes in it in our board. This is how a PCB board looks like. Let me zoom it. So here the uh, when we'll leave some points for drilling, we'll drill here, and for connections we will use soldering machine to solder the connection here to make them smooth. So here in the PCB, our PCB board was, and we use jumper wires. Let me show you how our connection over it was. So here were the ICs that were connected from upside, and this one was the view from downwards. So here from the jumper wires are connected to different components of the project. So main now coming to another point, another component which was used was motor driver. So motor driver acts as an interface between the motors and control circuits. A motor requires high amount of current, whereas the controller circuit works on low current signals. So the function of motor driver is to take a low current control signal and then turn it into higher current signal that can drive a motor. So this is the function of motor driver. And here in our project, we gave it. So we gave 12 volts our motor driver as and used the battery of 12 volts. We can also run it by by using our direct power supply, which can give it a constant power supply. But we can also use battery. So 12 volts were given to motor driver, and for the sensors and ICs, they were given the input of 5 volts. So that was the motor driver. Now let me show you the motor driver in the project. So this whole thing, the red and having some blue terminals here. This was the motor driver that was controlling it. So now we will come towards that IR sensors. We use IR sensors on it. So here was um, so let me explain you what an IR sensor is. An IR is known as infrared sensor, which is electronic device that measures and direct infrared signals in its surrounding environment. So this was basically discovered by an astronomer named William Herschel while measuring the temperature of each color. So here I will show you an IR sensor. Basically the IR sensor just emits some rays and which are deflected or reflected back from after hitting a surface, and a receiver receives it, and this will be used to give some signals to our other components that will perform operation according to it. So this is how the operation is done, that when active IR sensor had two pass LED, when an object come close to the sensor, the infrared light from the sensor reflect off the object and is detected by the receiver. So this is the IR sensor looks like. So in real, the IR sensor looks something somewhere around like this. So this was the IR sensor that we used in our project, and it has three terminals that are here, ground terminal, digital output pin, and one is VCC from where we gave the input. So we basically gave the input of 5 volts. Here is the IR receiver, and here is IR emitter. This one is the LED that emits the light on it. We basically used three sensors in front of it. I'll show you those. So here was I guess you can see it. The sorry, the picture is a little blurry. So here were the three IR sensors that were used and were connected to the battery sources and other sources. Now coming back to our presentation, this was the function of our motor driver. Now we will go to truth table. So here is the truth table that I'm going to explain you in the simulation part of our project. And this one was the Proteus implementation of our circuit. So let's move on to the Proteus simulation, and after it, I will show you how our project was running and how the operation was done. So here is our truth table for right motor and left motor, then under what conditions it will operate. So when coming towards our left motor, so we are given that when the input will be 0 and 0. Sorry, let me adjust it. Okay, that's it. So not really. Just a moment, please. So yeah, now just a moment. We will adjust it like this. Yeah, this would be better enough. Okay. So when coming towards the left motor, the for the left motor, the logic is that when all inputs will be 0, the motor will be off. So we will just 0 and 0. Now when we will simulate it, the motor will not operate. You can see that left motor is turned off. Now if we change it to that 0 0 0 and 1, 0 0 0 and 1, so we will operate it, and 0 0 0 and 1. Oh, wait. So we will just simulate it, and you can see that the motor has start its operation. Now coming towards our second, now we will see that when it will be 0 0 1 0, 0 0 1 and 0. So the motor will start operating. Right mode is 0 0 1 and 0 0 0 1 and 0. So you can see that the right motor is in operation. Sorry, my laptop is a bit slow, so it's not showing the simulation like it should. So now coming towards our, let's justify our this one when 0 1 1 and 0. So we'll stop the simulation and we'll change 0 0. Just a moment, please. Yeah. Coming back towards our circuit, so we were going to justify this one 0 1 1 and 0. So we will pause the simulation 0 1 1 1 1 and 0. Now we'll see that motor should not operate here, and we can see that motor is not in operation. Both motors are stopped here, and you can see the simulation part that here the motor is not responding when the simulation is running. So we will move towards some other. Um, let's justify now this operation when 111 left motor will operate. So and right motor will not be in operation. 111 and 0, 111 and 0, 111 1 and 0. So right when we'll see here, right motor will have 0, but left motor will be in operation. So we will stop it, we will run it, and we can see that left motor is in operation, but right motor is not giving us any response. So when left motor will be in operation, the line following robot will slightly turn, will make a turn. So this is the operation when for when a curved path will come where it have to turn toward right. So the motor, left motor will operate. or when the left motor will operate, so it and the right motor will not in operation, so it will make a slight turn towards right side, and right motor will be on and left motor will be off, so it will make a turn slightly towards left side. So that was the operation. Here now we'll justify some other one. So here 1 0 0 and 1 will give us 1 here, and here 1 2. So both motors will be in operation in that condition. So let us make it happen. We'll just stop the simulation, and which one was it? Yeah, this one. So 1 0 1. No, 1 0 0 and 1, and we will run it, and we'll see that both motors are in operation. And when the both motors will be in operation, then the motor will follow a straight path. It will move along the straight path, following the line on the path. So here is the conditions of left motor and right motor under which they will operate. So this is the Proteus simulation. Now we'll move towards our video part, that how our how our this project was in work in operation. So just give me a second. So this one is our okay. This one was our project. We were giving a direct power supply as the battery was drained out. So we were just connected it to a direct power supply and were giving it power supply. We can see that here the all the central learning operation. So it was giving us logic to follow it in a straight path, and both models were operation and were driven by the motor driver. So here you can see that how smoothly it was working. And when the curved path came, one motor stopped operation, and second one was operating to give it or allow it to move mm, in a curved path. So here was it, and it stopped right there. uh, at the moment it should stop, so it stopped it, and this was our project. So here there was some kind of mistake, or you can say some error, that in path or arena there were two lines. Like here when we come here, here it was this line two and this line two. So the our project was having some you can see when it came here, this sensor could sense this line and start the um, project to move along here. So I have that video to show you that how it changed the path. So let me show you that one, that you should avoid the mistake of making an arena such a way that both the lines will be close enough. So I'll show you that part now. So here we were when giving a direct power supply that was quite high for the motors to operate, and the motors were running in quite some speed. So then when I was telling you about the another path, that another path come across, you can see that when it was in operation. So here, right here, you can see that here it sends the another path, that there is another path, so it just made a turn and start following this path. So here how that happened, you can see it, and here, right here, it started to move along this plane. So that is a mistake, common mistake, that which you should avoid, that while you make an arena, make sure that the path would be clear and the other lines would be far enough from each other, so the sensor couldn't make going to sense the another path. So you will see the whole video that it made a side turn and started that path, which was totally wrong and it was blocked there. So you should avoid this mistake. And the second time when we saw that there is a mistake, so we just shifted the sensor position and changed sensor as it was hard to uh, change the arena. The arena was quite enough, big enough. So we just slightly shifted the sensor position to avoid it. And here you can see that the second time it right here it didn't sense that path and as it was having some distance, so it just made a well good turn here, stop right there. So that was how our project was in operation. So that and one more thing that I want to mention here, that we didn't use a chassis that was given in market, but we made our own. We just made a took a wooden card piece of cardboard and placed and made some holes in it according to our components, and we saved money from here. So as an engineer we have to keep budget in our mind too. So we this was kind of free of cost chassis. Other people use chases, like I can show you their part of video, like how they were using chases and it costed around 1,000 or maybe 1,200. But here we save that amount of money, and instead of using it we simply made our own chassis that was in budget. So this one was the plus point of our project, that we were considering budget too. So that was today. That was all for about today's video, and our how our project was made and what was the flaws in it and how we can avoid it. And all was this about the video, I guess. I hope you will enjoy the video. And if you have any query about it, you can directly just hit me up and text me asking about how any complication or any projects related query. So thank you so much for watching my video. Have a good day.